Good morning, everyone. Thanks, Chairman, for the introduction. So I work for GE, based in New York. There's a headquarters of the R&D center there. Now, yesterday, we had a great introduction of medical imaging. We heard a lot about clinical image quality. What is it? What are the clinical requirements? And today, later, we're going to hear a lot about technologies. What are the image sensor technologies? And I think it's the right time for me to talk about something about the detectors. How do we, what are the requirements of the X-ray detectors specifically? Again, the stage has been set right now in terms of the market, and there has been some mention of the flat panel detectors. The CMOS is, increasing the role in that flat panel detectors. So I think with that, let me talk about a little bit on the X-ray detectors based on CMOS for medical imaging. By the way, this is not a marketing pitch. I'm also not going to talk anything about a great technical breakthrough. It's more like a general introduction to detectors. So some of the questions yesterday were posed. I'll try to add a little bit of information on that. Now, if there is one message I want to leave with you today, it's this. It's that the CMOS detector technology is ready for X-ray medical imaging. And maybe it's a little bit of an overstatement, but I think what I'm trying to say is, it took a while, for this technology to get it mature for this market. And what I try to say is, what were the challenges, that prevented it to get there? And what does it mean to be ready for the medical imaging? And also, where do we go from here? So that's the kind of questions I'll be trying to address here. Now, the talk is outlined like this. Start with, and again, just for the completeness, one slide on clinical requirements, very short. A little bit on the X-ray detector technology. Yesterday, again, Inge had a good description of that. But focus mainly on the CMOS X-ray detectors. And finally, I have some outlook based on that. Now, in terms of requirements, let me first, for the general interest, try to explain what do we mean, what is the space of the X-ray detectors. Now, in terms of the systems, there are essentially 4 categories, starting with the radiography. This is where it all started. Primarily it comes in 2 flavors. This is this fixed room and the mobile systems there. Then we have the mammography. Again, mainly 2 categories. One is for 2D mammography, and the emerging trend is more for tomo because of some of the limitations of the 2D. And 2D, by the way, is the standard of care for breast cancer today. Now, then we have the surgery. This is more like the workhorse of the surgical image-guided surgical procedures. And there are different kinds of detectors and systems used there, but this is the surgical system. And then we have the interventional, which is more like the big brother of the surgery. It's a fixed room, a lot of procedures, interventional procedures. And one interesting thing to notice here that if you move from the left to the right, the radiography is primarily a static imaging. Mainly, it's about static images. If you go towards the mammography, again, 2D is static, but tomo you would like to go for, more like a CT kind of thing, a multi slices. In surgery, it's fluoroscopy, and then intervention is also fluoroscopy. Surgery, by the way, what distinguishes surgery is that it basically is a mobile system. So we have limited power and it has to be dynamic, which means it has a lot of requirements on the detector. For per image, the dose is pretty low. Now, from the requirements from the detector point of view, one thing it was clearly mentioned before, all of these systems use detectors are pretty big, huge in terms of a conventional CMOS image sensors. For example, the radiography, it can typically be 40 centimeter by 40 centimeter. It's huge. And mammography is also not too different. From a requirement point of view, high image quality, we have a good intuition what it means from yesterday's talk. It's about how well the detector can actually use information, the X-ray information. How can it transfer the signal to noise ratio? So that's what it means. The rest of them, the dynamic range, the spatial resolution, and speed, they're all kind of related to the image quality. But overall, we need to have a good detector. Now, from the detector technologies, let me give an overview of the technology. But I primarily focus on the DQE because that is, again, Inge mentioned yesterday, this is the most important metric. It's a metric for comparing one detector technology to another. For example, I mean, this is one of the tasks we always face. I mean, in my job, once in a while, a new kind of detector concept will emerge, and we are asked to, really evaluate. Is it really how much does it perform? I mean, is it really delivering what is promised? So this is one metric we can really use. It's a completely quantitative metric, and so I'll explain what are the nuts and bolts of that. But it's not the same as to talk about image quality. I mean, people have it's a little bit of misunderstanding. High DQE doesn't mean the image quality is good. It's only good for comparing one detector to another. Image quality is definitely dependent on the dose. I mean, so I'll try to make that a bridge between DQE and image quality. Now, again, detectors come in different flavors. We heard it yesterday. Essentially, there are direct and indirect conversion detectors. I focus on the indirect conversion because that's the main detector type. I try to give the information flow perspective and also the performance metric. And for the indirect detector, let me just quickly go through it. I mean, the X-rays come in. The first stage is converting the X-rays into optical photons. That is done by the scintillator, primarily by cesium iodide. Other scintillators are also being investigated. Once it is converted into light, then we need an image sensor. I mean, typically it's a flat panel. It has been the TFT morphosilicon panels, used for a long time. Now, after the array, we need some electronics to read out and to convert it into digital signal, and then we kind of make the image and then communicate to the system by the interface. So that is pretty much the information flow from a detector point of view. And as I said, the key metric is the detector quantum efficiency. It really a transfer of signal-to-noise ratio from the input to the output. And we saw that yesterday, how it is defined. I'll have more details coming up later, but it is kind of described in two dimensions. One is this, how does it depend on the spatial frequency, and how does it depend on the exposure? It's a measure of dose efficiency. And another metric that is often quoted is MTF, which is the modulation transfer function, which is a measure of resolution and sharpness. Just one point to remind here is it's rather easy to build a detector to have a high resolution. We just need to maybe have a little, decrease the scintillator thickness. That will easily give you a high resolution. But it's extremely hard to build a detector with a high DQE. So that's the challenge. I mean, I think people often, forget that. And DQE, in its definition, kind of already incorporates the definition of the MTF. It's a combined metric. So the key point here from this slide is, the DQE is the most important metric. And it's a high DQE is desired, and because you need to detect objects at low dose and low contrast objects. Now, just a little bit of deep dive on the DQE, because again, if you want to invest in a new technology, whether it's CMOS or whatever, we need to know what is the entitlement. How much can you go in terms of DQE? What are the physical effects that really constitute the DQE? Number here, there are 5 different physical effects, starting from the quantum detection efficiency. And it's simply, what is the stopping power? I mean, of course, the X-rays have to be stopped before they can be absorbed. I mean, they can be converted. So if you don't stop the X-ray, you're basically losing that much of efficiency. So that's the first step. It's easy to understand. The thicker the scintillator, you can stop. Then there is a swang noise, and there was a question yesterday, I don't remember who asked it, about the Lubert's or Lubert's effect. This is a little bit subtle. I think people, one thing we often forget is that the X-ray detectors here, we are actually basically estimating the number of X-rays absorbed in a pixel based on one number, the digital number, which is coming out of in a lot of processing. We are integrating the energy of the spectrum, we are converting that, and we're just transferring it to one number. A lot of information is lost in that process. So these two effects, the swang, noise, and lubberts, is really it's telling the information loss in that process. But what I'm trying to say is, if it is a photon counting detector, it will be much better. If it is a monochromatic X-ray detector, it will be much better. But the fact that we have an input, a spectrum of information coming in, and we just left with one number, and we have to kind of go back and calculate what was the X-ray, how many X-rays was absorbed, we lose information. And this is very critical when we actually develop scintillators and how we integrate with the detector. There are very subtle things we have to remember to make this swang, noise, and lubberts effect better. Then there is the aliasing effect, which is clear. We have to sample the information, the pixel. So that is well understood. And finally, electronic noise, again, which is we have an intuitive understanding of that. So out of this, first three are essentially driven by the scintillator. So, and the last two are by the image sensor. Now, again, as I mentioned, these are not abstract quantities. We can actually, fortunately, there is a well-defined standard, which is not the case in many other modalities, to be honest. I mean, we have a very good, well-defined IEC standard for measuring the DQE, and it's well documented. So I have a reference there also. Now, here's an attempt. This is just an artistic. I try to attempt what is going on. As I mentioned, there are two axes here. One is the spatial frequency, which actually tells you how much you can resolve any the image in different frequency. The other is the exposure. I basically plotted it as the inverse of the exposure so that it all starts at the corner here. Ideally, we would like to have a DQE equal to 1, irrespective of the spatial frequency or the exposure. It has to be flat number. Because it's a ratio, it cannot be more than 1. But you can easily see that there's a big jump there at the origin. It's already a big, let's give a number, 10%. You lose because of the QDE. We never can have a 100% absorbing scintillator, because that would require infinitely thick scintillator, because an exponential attenuation, isn't it? Then there is a 10% loss in the swang because of the factors I said before. It depends on the spectrum. It depends on the way you integrate the scintillator. So already they're at 80%. So that's the best you can get. And then if you go down in spatial frequency, because of the lubberts, the way the X-ray noise is spreading across the scintillator, that will drive the DQE down. And then you hit a kind of a wall at the Nyquist. That is the Nyquist aliasing frequency there. If you go down along the exposure, it is primarily driven by the noise. So this kind of a pictorial representation of what is going on in the DQE. And the message I want to give here is that the scintillator is one of the main components. No matter how best this image sensor is, even if it is zero electronic noise, it doesn't help, because we are only mainly driven by the scintillator. And then the two different fall off. One is frequency and one is exposure. These are the factors that control that. Now, again, as I said, the relation between DQ and image quality. So here, again, for illustration, so we have a plot of DQE as a function of exposure. And again, the ideal, the perfect detector is where the DQE is equal to 1. And it's a realistic detector is, as I mentioned, is about, 80% or 75% DQE at a high dose. And from there, if you go down in the exposure, you can see that I'm plotting two different cases here. One is for a typical flat panel. You can see that the DQE drops. And the other is when we have a panel with zero electronic noise. It's perfectly flat. Now, this behavior is well understood. And by the way, just to give you a flavor on this particular exposure range I'm talking about here, I think again we saw it yesterday, but this is kind of the range where the surgical procedures or the fluoroscopy, the low dose fluoroscopy is done. So it is important that we have a good DQE and at this regime. Now, okay, that is well understood. So in terms of the image quality, again, what I'm plotting here is the SNR, because the output SNR is what is important for the image quality, again, as a function of exposure. Now here, it is less dramatic, the change between a zero electronic noise and a typical flat panel is less dramatic here. By the way, the green plot is just a description that of an ideal detector. Even if you have a DQ equal to 1, this is just showing that the SNR is quantum noise limited. It's because the input statistics is a Poisson, and you can never beat that. You can only go like a square root of the dose. So here the difference between the flat panel and even the zero electronic noise detector is not that pronounced, you can see. So any statement of dose saving has to be related to this kind of a plots, not from the DQE plots. I mean, and there you can see that again, for the kind of exposures we are interested, you might save maybe 10%, 15% of a dose, because what it means is if you want to maintain the same output SNR, we can either operate in this the typical the orange curve, or we can operate in the blue curve. So there's a slight shift, and that is what is saving the dose there. Again, but the takeaway is that the scintillator technology is the biggest impact on DQE. You can see that it already dropped 25% there. I mean, because of that. And the second point is the electronic noise. So once we have that high dose DQE, then if we have a low noise panel, we can maintain that. That's the only thing a good panel can do. But the initial drop is already determined by the scintillator. And there is potential dose saving especially for very large patients, which they operate in that regime. There is some saving because of the panel. Now, because of limited time, let me jump into the CMOS. So starting with the kind of my own view of the image sensor landscape, just to connect the different people in the audience, trying to summarize the detector benefits and challenges from a CMOS perspective. And I would like to point out, I mean, what are the challenges to build a CMOS detector? And then finally, if I just talk about this, these entitlements and performance, it's not very convincing. So I just want to leave you with a recently introduced product from GE, the OEC Elite CFT. This came out, I think, a couple of months back. This is our premium surgical SIAM. So we basically have replaced the image intensifier with the CMOS. So I mean, I've been in the part of the team that helped in this program. So it all comes together. So with that, the technology landscape, I mean, there are different ways to dissect it, but I chose to look at from a material technology on the x-axis and the pixel complexity on the y-axis. Again, this is the imager landscape. So obviously, the main players are the amorphous silicon and then the crystalline silicon. And from a performance point of view, it's clear. I don't have to talk about it. I mean, obviously, crystalline silicon, the CMOS technology, it helps for higher integration of electronics. It can, faster devices, and again, from a material point of view, it's important for X-ray that there is no lag, because this is one of the issues, especially for amorphous silicon. If you want to push it for very high frame rates and applications which is beyond X-ray like CT, I mean, if you think about it, I mean, the lag is a big issue. I mean, we heard a little bit yesterday. Now, if you look from the pixel complexity, again, the traditional flat panels are passive pixels, like one, the photodiode and the transistor, just a switch. But an active pixel, which has an amplifier inside the pixel, it essentially helps to drive the noise down significantly. I think you'd be surprised. I mean, even putting a simple transistor in like a 3T transistor architecture, these classic APS, that will cut the noise by a factor of 10. I mean, to give an idea, in a TFT panel, the noise is like about 1600 or in that range, 1500 electrons. I mean, in a typical flat panel. It's very easy to make a 150 or 100 electron noise CMOS active with this 3 transistor, the simplest of pixel design. So that is huge, and that is also helping for readout and pixel level processing and a lot of other potential different ways of operating, like a non-destructive readout and a lot of other things that can happen. Now, again, in this landscape, the amorphous silicon TFT, that is where we are today. I mean, from a typical X-ray flat panel in that quarter. And for the CMOS panels are operated in the classic APS. That doesn't mean that there is no room for going up. There are a lot of opportunities like global shutter, digital pixels. So it's just the beginning. I mean, we just at the point where we kind of solved some of the fundamental issues of building a detector. But I think my feeling is that now it's time to look further and see, integrate more, potentials in the pixel. So it's the imager benefits not only from the material quality. That is very important. The lag, it's got a good material to start with. Which means you don't have to worry about any raw correlated noise or lag and things which has been a big problem with the amorphous silicon panels. And then we can also leverage the advanced pixel architecture. So with that, how does it differ from a typical flat X-ray amorphous silicon detector? So basically, what I've done is you replaced the the panel. And also you integrated, you basically combine those two parts into into a CMOS imager. That really helped because it less number of parts, less, more integration. But there is also room to grow in the other aspects too. And because of the integration, we have low electronic noise, high speed, high EMI immunity. This is again an understated problem, in many applications, and also high spatial resolution. And this is, I'm showing the entitlement, so again, for exceptional low noise performance. So what I'm showing here is if you put a CMOS detector out there, I think from an entitlement perspective, to achieve a 0.1 X-ray noise, what does it mean? Noise. One important thing to remember is when you talk about X-ray detectors, we're not interested in light photons or electrons. We're interested in X-rays. So everything has to be converted into X-rays. And the conversion unit from the electrons to the X-ray is determined by the scintillator. How many electrons are created by one X-ray photon? So in that unit, we have about 0.1 X-ray. That is possible with CMOS compared to 1 X-ray in TFT. So that really determines that the drop in DQE is significantly low. By the way, if you saw some of the presentations yesterday, this drop was a little bit more aggressive. There are reasons behind it. I don't want to go in right now, but this is the entitlement. Just to remember that. And again, that was in the axis of the exposure, but in spatial frequency, it's rather easy to go for a small pixel. It's no brainer. I mean, we're talking about 1 micron pixels today, so building a 50 micron pixel is not a big deal. So that will really help in extending the resolution. But the real question is, okay, we have this extended range, this new domain. What do we do with it? I mean, what is the clinical benefit? That's a more challenging question. I mean, we need more work to understand that. I mean, can we see more microcalcifications? Can we classify them? So these are questions it takes time. But first, we have to have the detector out there and test it. But we have this capability of doing that. So it's fair to say that it really pushes the limits of detection from two aspects. One in terms of sensitivity, and it also pushes in terms of the spatial resolution. We have to really work on what are the clinical and new applications that will come out of this. Now, that was all well and good. I mean, we have a great detector, a great sensor, but how much? 3 minutes, oh man. So, you can see that. I mean, it's what I want to illustrate here is the size. The single unit there is a full frame CMOS sensor, which is pretty big from a conventional CMOS point of view. You can see that to build a typical 30 centimeter panel, we have to have almost like 100 of such sensors. So that's the size you're dealing with. And that is only the middle range. And then there is also the 40 centimeter. So it's pretty huge. But we solve that problem by tiling. And so you start with a single wafer. You cut the biggest tile you can have, make it three-side buttable. A lot of technology behind it. I don't have time to do that. But we made it. So basically, we can build the middle one is a 20 by 20 centimeter. This is a 30 by 30 centimeter. We can go in this direction, x-axis to any because it's a three-side buttable design. You can go in any length along this direction. But this vertical direction is limited by the wafer size. So if you have a 12-inch wafer, you can easily build a 40 centimeter panel. So that's the size. Maybe I can skip the dynamic range. We talked about it yesterday. There are ways to deal with the dual well design. But the one thing I point out, there is an interesting way we can operate this the CMOS sensor for applications where, like mammography. I mean, the traditional view is that you design a detector for the highest saturation level. But then we are forced to operate it for a tomo, which is like 1/10 of its saturation. So that's definitely suboptimal. The best way is basically to design it for the lowest, the dose per frame, and then just run it like a fluoroscopy detector. So that's what I show it here, like a multi-frame read. You can easily acquire like a fluoro detector and basically sum the images. And obviously there is a noise penalty, but we don't care because usually what happens in a 2D mammography, you're not noise limited. So there are many ways to solve this problem. And last minute, I think the cost is definitely a concern because the wafers themselves are expensive. But my takeaway is that this is just the beginning, and there are a lot of ways we have to manage the yield, because it's unlike consumer electronics or scientific pixels. We have pretty large real estate to deal with. We're talking about 50 micron, 100 micron pixels, a lot of room. So maybe the traditional metrics for yield doesn't have to apply in X-ray. We can apply redundancy. We can do the definition of bad pixels, and things are defined by the medical requirements. So there is room to grow there. Here, I just want to mention there are different, beyond the wafers, there are also costs involved in integrating the detector together. There are different ways to do that, and with the different advantages and disadvantages. I leave it there because of time constraint. I just want to introduce this, the one slide, the product I was talking about. This is the premium CARM system from OEC, introduced in Europe a couple of months back. So what you're looking at is a 30 centimeter by 30 centimeter detector. So that what I was showing before, based on CMOS, 2x3 tile detector. And to leave you the outlook, again, it's very difficult to predict it. But what I see is there are two ways it can grow. One is to expand into other modalities. It doesn't have to limit to surgery, because that is the best choice from a CMOS point of view. It's a low-dose dynamic imaging. But it can grow into mammography. There is no reason why not. You can make use of the high resolution. It can go into interventional because of the high-speed dynamic imaging. There's nothing limits there. And also CT. I mean, I'm also working in 3T these days, and I don't see any reason why not. It can also grow into alternate scintillators, because all the designs of the TFTs today were optimized for the, all the scintillator of today's cesium iodide was optimized for TFT performance today. But that doesn't limit the space of scintillator. When you introduce CMOS, which has high sensitivity, I believe that it basically expands the space of scintillators. I mean, we should look for more materials which are, from an X-ray perspective. So I think that is an area we should definitely look into. But the key to success is really low-cost panels, and you are the experts how to deal with that. And then from a clinical perspective, you need to add more killer applications to it, like a color X-ray. We have all the electronic integration experience out there. You can add any kind of functionality, so why not? If we can build a large area detector, why not we add all those functions? So in summary, it pushes the limits of detection. I think it's ready for prime time. And we should expand it to different scintillators and modalities, but we need to cut the cost down for the success. And so I want to leave you with the first image where it all started, and thank you for your attention.